Today we are going to do section 6.1, the vector fields. The vector on page 643. Now before we do vector fields, let me first remind you what a vector is. Now a vector is something that starts at some point, okay, and then ends somewhere else. The way we represent it is taking the end point, the terminal point, and subtract it by the beginning point, component by component. For example, this vector v will be 4 minus 1 for the x component and 3 minus 1 for the y component. And then we write these, brackets here to represent it. Another way to represent it is write down 3i plus 2j, where I is the x direction and j is the y direction. And then eventually in 3D, then we even have a k for the z direction, but the principle is the same. So that is how you calculate a vector. Now a vector doesn't normally have a location. We just it only have a direction and a magnitude. That is how long it is. The magnitude is calculated by the Pythagoras theorem. That is 3 squared plus 2 squared, and then you take the square root. However, that's the length of this thing. However, in this section, we're going to put the vector somewhere, okay, specifically, which is okay. I mean, you can pick up the vector and put it anywhere. As long as its direction, its magnitude, it stays the same, it's the same vector. It doesn't matter where you put it. So we're going to put it somewhere else. Now please look at page 643, definition. What is a vector field? A vector field is a function f(x,y), okay, the f is in boldface to mean that the result is a vector. The result of the function is a vector, okay? So what does this vector function do? Well, it given any point in xy, in the xy plane, then the function will give you a vector for that point. For example, let's see you have a point, right? And then that point, the function you stick, it has an xy coordinate in there, and then you will stick x and y value into the function, and out pops a vector. You will kick, at that point, it will point that direction. And then if you pick a different point, the function might spit out a vector that points at a different direction. And not just point at a different direction, it also might have a different magnitude. So then you might have one that goes like that and one that goes like that. As you input the value of your coordinates, x and y, for different spots, the function will spit out different vectors. That is called a vector field, which just means a function that takes values from your plane and then spit out some kind of a vector. Now, of course, it's also possible to have a vector field in 3 dimensions. That means it's a function that takes spot in your 3-dimensional space and spit out some kind of vector pointing some direction in 3D. So to see an example of that, let's look at example 6.1, and where, I should first mention that the function is represented the same way a vector is represented. That is, you can represent what is this function called? I forgot already. It's called a vector field. Okay, the vector field function can be represented like with a bracket. Okay, that's the result where you plug in x and y. P and q are just regular functions. They'll spit something out similar to this thing, right? And then, or it can be written in the I and j condition. So that the first one represents the x component, and the other one represents the y component. Now, as an example, let's look at example for 6.1. You have some kind of a function, okay? I mean vector field function, and then and you're gonna is in 2D. That's what that R2 means. And then what happens? What's the vector at 0, 1? Well, you just plug in 0 and 1 and come up with some vector, because that's the definition of the function. So you plug it in, out comes some vector, and that is the answer of the vector at that point. And so it's, as you can see, quite straightforward. And that's example 6.1. Please do that as part of your homework. Now, as you can see, eventually you're gonna be drawing all kinds of stuff, right? As you plug in each point, and then you end up with all these vectors pointing all kinds of directions, and that is how you draw a vector field. Now, there are 2 kinds of vector fields that we specifically focus on. The first one we have here, I'm now on page, the following page for 644, and then it mentions something called a radial field. The radial field is a vector field where all the vectors point away from the origin perfectly. You know, it's like the sun shining, the lights, the sunlight that's just all come out every direction out of there. Straight out of there, that is. And that's, if that happens, that's called a radial field. The radial field, let's look at example 6.2 on page 645, where we have a radial field. Actually looks like, what is this? It's just x and y that are the same value, x and y have the same representation, basically. See, here's a radial field, and what is it? It is x over 2I plus y over 2j. Now, when you imagine drawing this thing for values of x and y, you notice that x and y are the same value, so then it's very likely that it's just gonna go, well, you can calculate its slope to see that it goes exactly straight out of there. Okay, the way you draw vector fields, of course, is you just pick different points, and then you come up with what your vectors are. And for example, like, let's see, we'll draw a couple. Okay, for example, like, let's say, what happens when x is 1, y is, let's say x is 1 and y is 0. What happens when x is 1, y is 0? 1, 0. All right, here's our field. At 1, 0, the vector should be 1 half and 0. So your little vector might point like that, right? And then what happens at well, let's do this one. This is 1, 1. Okay, and at 1, 1, your vector should be going 1 half, 1 half, which is like 1 half, end up like that, right? And so on. So now that we've drawn 2, we've done enough. I mean, I've done enough. So the rest of it, we are going to look at the results for a second. So look at the next page. You will see the vector field being drawn. See, if you draw the vector for every single spot that you see there, then you see this radial field. And you can see why it's called that. It's because everything goes straight line away from the origin, which is where the sun is. And furthermore, you also notice that if you have to draw circles on it, circles that are centered at the origin, then you notice, of course, that being this thing going straight out, all the vectors are perpendicular. That is, what is this called? Normal or something? Yeah, they just call it perpendicular. All right, so all the vectors are perpendicular to all the circles, being that it is a radial field. All right, so, and you might think, are we really gonna do that many vectors? No, we are not. Take a look at this. I have the link for drawing the vector field below in the video description. And as you can see, to draw it, you go to the link, and then you change the function f. Where's my hand? Oh no. Anyway, you change the function. They have a function already typed out for you on this side. So right about here. Okay, and you just change it. In our case, it's x over 2, y over 2. So you change that to that, and then this thing will pop right out. See how nice it looks? It doesn't have circles. The circles are in there because I added them down here, but you can't see it here. You just scroll it down and then add the circles. And how do you add circles? You just type in the radius. You just type in this. R equals to 0.5, that's my first circle, and R equal to 1 is my second circle. R means radius, okay? And the Desmos is very smart, is that all you have to do is do that, and out comes your circle. See, I have R equal to 0.5, and can you see the 0.5? And then the other one is R equal to 1. And then as you can see, the vectors are all perpendicular to the circles, normal, I think. Well, whatever. The point is, that's how you're going to be drawing this stuff, okay? But it might not hurt to draw like 1 or 2, just to get a feel for it and see how this works. Anyway, so let's keep on. So that is example, whatever this is, example something. Can't find it. 6.2, yep. So please do example 6.2 as part of your homework. That is, please type this thing in yourself, okay, the function, and be sure that you, reproduce this thing, and then you can zoom it in, zoom it out, and see it, and all those things, and see how it looks. It's very, very neat, because you don't have to do all those plotting of how many vectors are there, but you don't have to do any of it. That's the beauty of the story. All right, and then that's that. And where's that? Okay, the next page. Let's go to the next page. We are now on page 647. Well, we consider the rotational field. Now, we just looked at the radial field where things go straight out, right, out of there. Rotational field is something that goes around in circles. It just which sort of remind you of, hurricane, of course. Here. In fact, there is let's look at example 6.3 on page 647, where we have a picture of a nice little hurricane there. And then, but more importantly, the function. Okay, you notice the vector field, the rotational field, is just y minus x. That's all it takes to create a rotational field. So you plot it out, okay, and then, but maybe do a point or two just to get a feel for it. And then the rest, let's do it on the Desmos calculator, and then you get something like this. Well, the book provides a very small picture, but the idea is the same. You see, you notice that the thing just goes around and around. Everything is chasing around the thing. And then eventually what you have is if you draw circles on it, that is on this side, you notice the circles, and then all your vectors follow the circles nicely. But what happens here? Here is when you have two vector fields together, okay? And that's why it looks so weird. They're actually two vectors, because they want to show you that the radial field and the rotational field are always, the vectors at the same spot are perpendicular to each other. So, and how do we know they are perpendicular? One way to prove they're perpendicular is taking the dot product, which is right here. Now, if you have the original vector field that's AB, and this new one we are doing, which is minus BA, that's our vector field, okay? And then you take the dot product, and well, they become 0. And if the two vectors dot product becomes 0, that means they have to be, they have to be perpendicular, right? And then the vector has each vector has the length of the square root of your Pythagoras theorem. So sometimes you can, anyway, so that's the length of each vector, and having and the length will be given as r. R is the circle. Okay, if you type in r equals to some number, then you draw a pile of circles on your vector field, and that's that. So that was what was that? Was this? This is example 6.3. Please do that as part of your homework. Just plot it on the Desmos calculator and look at and stare at it a little bit. And next, let's look at example 6.4. Yet another vector field. All right, which end up being something like this, which is, it's slightly different, and I guess it's spinning around like that. Well, sort of like, I don't know what that is. It's a rotational field, of course. So you crank that in, and so please do 6.4 as part of your homework. Example 6.5, the same thing. You do something, and then and then 6.6 the same way. A unit vector field is something that you have to divide by the you normalized it. That is, which means did I say normalized? Whatever. The point is not normalized, but you made it, turn it into, each vector has to have the unit of 1, which means you divide it by the length, the magnitude. See, like this function in x vector function field function in example 6.6, it gives you an example of a unit vector field because each point is being divided by its magnitude of the vector. So that will show you to be 1. So that's example 6.6. And then next, let's look at vector fields in 3 dimensions. Now let's look at page 652, where we have example 6.7, sketching a vector field in 3 dimensions. Now doing things in 3 dimensions are just one more variable of the 2 dimensions, but everything else goes exactly the same. So as that example can clearly show you, please do that example as part of your homework. And now notice that when you plot this thing out, I have the link for 3D vector field in this video description below. Now when you plot it out, you might notice that the graph doesn't much look like what is shown in the book. Okay, that's because you have to adjust certain things, dimensions, space between, that sort of thing. Anyway, here's what I did. Now you notice that here's our function, okay, which is 1,1z, right? A very, let's see, which way am I moving? There, 1,1z, a very simple vector field. What you need to do is to make it look like the graph in the book, you need to change z. This is at the bottom. I mean, you need to scroll this thing up, okay? And this will show up down there, and then you adjust the z from into -3, -2, etc. to 3, that kind of thing. If you stare at it enough, then you'll see what that is about. The point is, go ahead and change that. Then your vector field will look more like the one in the book. See, here's what I got, which is similar to what you have in the book. You notice the vectors are flowing up, and then it's on top, and then it's flowing down on the bottom, and so on. Just like, let's look at what the book has. The book has a similar thing. See, it looks like it. But make sure you make the adjustments. Otherwise, your vector field looks a bit all crammed together, and you can't see, and it doesn't look quite right. All you have to do is just adjust the dimensions and all the stretching of the numbers. Okay, all the ranges, and then it'll look just right. So please do example 6.7 as part of your homework. Example 6.8, same thing. The gravitational field, you just well, this one doesn't have any numbers, but the principle is the same. You have, does it have numbers? Whatever, just do that, okay? It's the gravitational field. It's a vector field it's a radial field that all goes into the sun, but otherwise is no different than what we've done before. All right, so then next, we are going to look at gradient fields. Gradient fields, also called conservative fields. Either way, what that means that is made by the gradient. Now, what is a gradient again? Now, a gradient is when you take the partial derivative of a function. Let's say you have a function of x and y. Okay, there is a function of x, y, f. Then the gradient of f is defined as the partial of f with respect to x in the I direction and partial of f with respect to y in the j direction. That's the gradient. In 3D, then you have one more direction, k, but the principle is the same. You take the partial derivatives with respect to x for I direction, y for j direction, and z for the k direction, and that was the gradient. Now, a vector field, now some function f is a vector field. Let's look at the definition. Now, did I mention what page we're on? 654. I should probably write that down. Okay, so we're on page 654. And then let's look at the definition. A function f is a gradient field, also called conservative field. Either one, it is a gradient field if there exists a scalar function f such that the gradient f happens to be the vector field f. That is, if the vector field comes from some function and you take the gradient out of it, then it is called the gradient field, also called the conservative field. So that is so that's how you know something is a gradient field. It happens to be the gradient of something. Okay, basically is what that means. Okay, so let's draw the gradient field. Well, to draw the gradient field, example 6.9, you have to you're given a function f, some generic function. Yeah, you're given the function f, right? The book typed it twice. And you can just forget one of those, okay? F of xy is, say, x squared, y squared. You take the gradient, and that becomes your gradient field, the vector field, and then you type into decimals, and out comes your gradient field in graphic form. So that's that. So please do example 6.9 as part of your homework. Next, let's look at page 655, where we have considered the function fxy, which we just looked at, the one that's x squared, y squared. Now, we just plotted the gradient field of that thing, but remember that we can also plot the level curves. The level curves are where the function equals to various numbers, right? From 0, 1, 2, 3, etc. That shows us how the function is rising from the ground. So the level curves are all the lines that the function is level. Okay, and then so as the level curves build up, then you know that's where there's a mountaintop at that point. Now the notice that it happens that being that the gradient is perpendicular to the level curves, the vector field then is always perpendicular as well, being that the vector field and each of these vectors is the gradient. So you can see the gradient happens to be exactly the gradient, the vector field is perpendicular to the level curves. And then when that happens, that is, in the situation where the gradient of f is equal to the vector field f, then the small f is called a potential function for big F. That is, it has the potential of becoming the gradient for the big F. Okay, so that's just a name. It's called a potential function. So please do example 6.10 as part of your homework. And 6.11, same thing. Check that something is a potential function. Yeah, well, go ahead and take the partial derivatives, right? And so then that get us to page 657. Now let's look at theorem 6.1 on page 657. At this point, we are considering the uniqueness of potential functions. Potential functions are little f that can become big F. Okay. Now, if you have a big F, which is a vector field function, and then is on some kind of a good situation where it is on an open and connected domain. Open means it anyway, open means it doesn't contain it. Every point inside contains a neighborhood that's also inside. Okay, and that is nothing's on the border. Every point has its own little neighborhood that's all surrounding it. That's what open means. Connected means it's not disconnected. That is, it's not in two chunks. It's in one chunk. Okay, and anyway, so let f and g is so we have two functions such as the gradient of both functions becomes the vector field function. If that is the case, then f and g are only different by a constant. Now that seems reasonable because the gradient of f is taking partial derivatives. So you can imagine why it would be unique only up to a constant, right? If something else, the gradient is the same thing, they must be only different by a constant because that's how derivatives work. If two derivatives end up being exactly the same, they must be only different by a constant. Now that's the vague idea. The actual proof is not much harder. So please do this proof yourself as part of your homework, theorem 6.1. So next, let's look at theorem 6.2, the cross-partial property, which states that if you have a vector field that has continuous second order mixed partial derivatives, that means that's actually not quite right. What it should be said is that its potential function, little f, has continuous second order mixed partial derivatives. Okay, yeah, please remember that the small f is instead of the big F. That is, the potential function has this mixed partial derivatives that we want. Not that it really matters at our stage, but I just want to be clear. We're not talking about the big F having continuous mixed partial derivatives, we're talking about the small f, that is its potential function. Now, and in this case, we're only talking about conservative or gradient fields. Okay, so then if the little f has continuous partial mixed derivatives, then this particular situation happens. An interesting deal, which is a partial. For example, if f equals to x, let's see, what is that? P xy and q xy, etc. Then partial p partial y is the same as partial q partial x. Why? Because f is the result is the result of is the gradient of something, and the proof of that uses the fact that if the mixed derivatives of the small function, see, that's why I said that we're talking about the mixed derivative of the small function being continuous up here. Right, now if the mixed derivative of the small function is continuous and all, then there is a theorem a few hundred pages ago that says the mixed partial derivatives such as fxy and fyx are the same. Very convenient. Okay, it doesn't matter which way you order it, and as a result, that is how that translates into this part. That's the same as saying that partial p partial y is partial q partial x. Now, so please prove this theorem as part of your homework. That's quite straightforward once you write down what everything is. For example, f of x is equal to p. Okay, now once you did that, then you can see where the thing applies in the proof. Basically happens in one step. It's one of those neat proofs. So please prove theorem 6.2 as part of your homework. And then let's move on and look at example on page 658, example 6.12. Now in this example, you notice that you're trying to prove that something is not conservative. Now we should read theorem 6.2 more carefully, which says that if something is a gradient field, then its partial derivatives has that quality of being equal. It doesn't say the reverse way. That is, if something's partial derivative are equal, it doesn't necessarily make them a gradient field. Okay, the idea goes one way only. Gradient field means partial derivatives are equal. That's it. I mean, some partial derivatives are equal. The one with respect to, well, anyway, yeah. So remember, you have to apply this theorem very strictly, as all math theorems, that you have to apply exactly as it says, and you cannot go some other way and expect to get away with it. So in other words, because of that theorem, that means how do you show some vector field is not a gradient field or conservative? It's not a gradient field if those mixed partial derivatives are not equal. That's all, because all gradient fields have equal partial derivatives. And that would be example 6.12 and 6.13. And so please do those as part of your homework. And we have come to the end of this section. For homework, please do let's see, I can't find it. Go down. Okay, for homework, please do problems on page 660. Please do problems 3, 9, 13, 17, 21, 25, 33, 35, and 37. Now the problems are pretty, are very short and simple. You know, we're starting out the chapter on easy, so I'm just gonna show you quickly. I did a couple of them for no reason. See, as you can see, they're very short. No, not much worth talking about, but you can look at it. I don't know that you need to. But anyway, so that's about it. They're not really worth mentioning. So that marks the end of this section.